Welcome to Computational Approaches in Physics Learning. Today, we extend our data manipulation skills to structured scientific text data, specifically coordinate files and simulation logs. By the end of this lecture, you will be able to parse complex file formats like XYZ and LAMMPS logs, convert them into pandas data frames, apply physical filters, compute derived quantities, and validate your process data. Let us briefly recap our workflow. A reliable process involves inspecting, cleaning, filtering, and validating data while preserving the raw source. We begin by importing standard libraries like NumPy, Pandas, and Matplotlib. Scientific files are rarely simple, comma-separated tables. They often contain header lines, repeated blocks, and mixed metadata, which require custom parsing logic before we can analyze the numerical content. Consider the XYZ coordinate format, common in molecular physics. It uses repeated blocks, where each frame starts with the number of atoms, followed by a comment line, and then the coordinates. We define a sample 3-frame string to practice on. Continuing our sample XYZ string, we see the second block representing the next time step. It again starts with the atom count and a comment indicating step 100. The final block in our raw text output reveals the coordinate data for step 200. Notice the regular structure, but pay close attention to the numerical values. Specifically, the final carbon atom at step 200 has an x-coordinate of 15 angstroms. This is significantly farther out than the rest of the molecule. We will design our workflow to flag this instead of blindly deleting it. To parse this dataset, we write a custom function that reads the block structure. It isolates the step number from the comment line and begins looping through the file to extract individual atom rows. The parsing logic strictly checks that the number of rows matches the declared atom count for each frame, raising an error if the file is malformed. It then splits each row into a label and 3 spatial coordinate values. We compile these extracted pieces into a list of dictionary records, capturing both the metadata, like the frame index and step, alongside the physical coordinates. Finally, we execute the parsing function on our text and convert the resulting list of records into a pandas data frame, providing us with a clean, tabular representation. The resulting data frame perfectly aligns the hierarchical XYZ data into a flat table. Every atom now has its coordinates mapped directly to its corresponding time step and frame index. With the raw text successfully transformed, each row now contains both the tracking metadata and the specific atomic information, making the dataset ready for computational analysis. Before diving into physics, we must inspect and validate the parsed data to ensure internal consistency. We print the shape, check the data types, and count the atoms grouped by step. The diagnostic output confirms we have 15 rows with no missing values, and exactly 5 atoms successfully parsed for each of the 3 time steps. We can formalize this with a validation function that explicitly checks for all required columns and verifies that the counted atoms match the expected number declared in the file headers. Running this validation function prints a success message, giving us confidence that our custom parser correctly interpreted the XYZ blocks without silently dropping or scrambling data. Next, we compute derived quantities. A standard check is calculating the distance of each atom from the origin using the Pythagorean theorem, which helps us flag suspicious coordinates mechanically. The updated data frame now includes a radius column and a Boolean flag column. As expected, the carbon atom with the 15 angstrom coordinate correctly triggers our distance flag. To review the anomalies, we filter the data frame using the Boolean mask to display only the rows where our coordinate flag is true. The output confirms that a row has been flagged for having a large distance from the origin. We clearly see the specific carbon atom at step 200 that exceeded our 6 angstrom threshold, allowing us to isolate and review its physical validity. Importantly, we merely flagged this row rather than removing it. Depending on the simulation, an atom far from the origin could be a real feature, a periodic boundary artifact, or a genuine error. We often need to isolate subsets of data. Here we demonstrate filtering by a specific time step, by an atom label like oxygen, and by a spatial bounding box near the origin. The printed outputs show the row counts for each subset, confirming that our logical filters successfully captured the targeted physical conditions. Displaying the step 100 subset shows only the atoms from that specific frame, verifying that our temporal filter works correctly. To avoid silent errors downstream, we write a helper function that raises an exception if a filtering operation produces an empty table. Testing our subsets through this helper function confirms that all our physical filters returned non-empty data frames, meaning it is safe to proceed to plotting. Visualizing the coordinate data helps us verify molecular geometry and spot outliers. We initialize a scatter plot, grouping by atom label to assign distinct colors. The resulting plot reveals how the flagged carbon atom severely stretches the horizontal axis. This extreme scaling visually confirms why checking coordinate ranges is crucial before further analysis. To see the core molecule clearly, we create a new data frame that applies a logical NOT operator to our coordinate flag, excluding the outlier, and then generate the scatter plot again. With the outlier excluded, the bent geometry of the simplified molecule becomes clear. The spatial relationship between the oxygen, hydrogen, and carbon atoms is now properly scaled and visible. Keep in mind that we excluded the suspicious row solely to improve the visualization. The original parsed table remains fully intact for record-keeping and further diagnostic checks. In molecular dynamics, pair separation is often more physically meaningful than absolute coordinates. Let us calculate the distance between the oxygen atom and each hydrogen atom for every frame. We loop through each time step, identify the oxygen and hydrogen rows, and compute the Euclidean distance between them, accumulating the records to build a new data frame. The resulting table gives us a clear time series of the oxygen-hydrogen bond lengths, distinctly tracking the two separate hydrogen atoms across the simulation. To observe how these bonds behave over time, we group the new data frame by atom pair and plot the separation distances against the simulation steps. The plot shows the evolution of the bond lengths. They remain highly stable, exhibiting only slight fluctuations, which indicates that the simulated molecule is holding its structure. Because the distances stay near 1 angstrom, the values are physically sensible for an oxygen-hydrogen bond. A sudden jump would immediately alert us to a bond breaking or numerical instability. Another common task is converting between different scientific formats, such as turning a fixed-width PDB file into an XYZ file. We define a small PDB-style block to demonstrate. The raw text is printed here, showing the rigid column structure typical of PDB formats, containing atom numbers, element labels, residue names, and spatial coordinates. We write a parser that slices the text using Python's string indexing. Because PDB is fixed width, we know exactly which character positions hold the element symbol and the floating point coordinates. The parser successfully extracts a clean list of tuples, each holding an element string alongside its extracted x, y, and z coordinates. We then write a formatting function to convert these tuples into the standard XYZ layout, appending the total atom count and a comment line before formatting the numbers. The printed output displays the newly constructed string. This confirms we successfully reformatted the rigid PDB data into the flexible, space-separated XYZ structure, making it ready for export or downstream visualization tools. Moving beyond coordinates, simulation outputs like LAMMPS log files contain a mix of setup text and numerical tables. We create a mock LAMMPS log to practice extracting the thermodynamics table. The printed log shows arbitrary text at the top, a line specifying physical units, the table header starting with the word step, the numerical trajectory data, and a closing performance summary. Our parsing function scans the text line by line. When it finds the keyword step, It saves the header and sets a flag to start collecting the numerical rows. The collection loop stops automatically when it encounters the word loop, ensuring we only capture the actual simulation data. We then construct a pandas data frame using the saved header. The resulting table isolates the numerical simulation data perfectly. We have correctly labeled columns for quantities like potential energy, kinetic energy, and total energy. We perform a quick inspection to extract the column names as a list and check for any missing values that might have resulted from parsing errors. The output confirms that all our expected thermodynamic columns are present and completely populated, with 0 missing values across the dataset. To analyze the thermodynamic behavior, we plot the system temperature against the simulation step. The graph shows a smooth decay curve in temperature over time. This represents the physical system cooling down and losing kinetic energy as the simulation progresses. We perform a similar visualization for the potential energy, extracting its column and plotting it over the same sequence of time steps. The potential energy curve closely mirrors the temperature trend, dropping rapidly at first and then beginning to level off as the system relaxes into a lower energy state. To directly view the relationship between these two thermodynamic quantities, we create a scatter plot plotting potential energy directly against temperature. This phase space plot illustrates a clear positive correlation, giving us a direct view of how potential energy scales with temperature during the cooling process. This correlation is physically sound. As the system cools toward equilibrium, the kinetic energy drops, allowing the atoms to settle into deeper, more negative potential energy wells. Diagnostics are just as critical for log files. We write a validation function to ensure all required energy columns are present and that the time steps are strictly increasing monotonically. The validation routine passes without errors, confirming our log data is sequentially consistent and structurally sound. As a final physics check, we verify energy conservation by comparing the reported total energy against the sum of the potential and kinetic energies. The maximum absolute error is exactly 0. This mechanical check confirms that the simulation's energy accounting is perfectly consistent within numerical precision. Let us review common pitfalls. Manually editing raw files, ignoring units, or skipping validation checks can easily lead to silent errors. Always keep raw data untouched and programmatically document your cleaning steps. Now we apply these techniques in a guided practice. We will combine filtering, validation, and grouping on the datasets we just parsed. The output shows that extracting the carbon rows yields 6 entries, while combining the time step and validity filters isolates exactly 4 reliable atoms at step 200. The output table displays these 4 valid atoms, proving our combined logical conditions successfully bypassed the anomalous 15 angstrom coordinate. By grouping the coordinate data by atom label, we can compute the mean radius from the origin for each element type across the whole trajectory. The resulting aggregation gives us a compact summary of the spatial distribution, showing that the carbon atoms orbit much farther from the origin than the oxygen and hydrogen atoms. Returning to the LAMMPS data, we filter for the later stages of the simulation by slicing for steps greater than or equal to 200, and prepare a plot of the total energy. The non-empty filter check passes, printing that 4 rows were successfully captured in this late-stage slice. The resulting plot zooms in on the tail end of the energy relaxation, showing the finer details of the equilibration process without the distraction of the initial steep energy drop. This guided practice demonstrates how programmatic subsetting and validation allow us to cleanly isolate specific chemical species, timeframes, or physical regimes for targeted analysis. To summarize, data manipulation is a core component of scientific reasoning. By structuring your parsing, filtering, and validation as code, you ensure your analysis is reproducible, physically sound, and robust against hidden errors.